When you look at a modern utility-scale renewable facility, you see thousands of solar panels and megawatt-scale battery storage units. However, getting these massive sites safely connected to the wider grid requires solving a microscopic problem inside the equipment itself. That problem is magnetizing inrush current. At the exact moment a transformer is energized, it can draw an asymmetrical surge of current that significantly exceeds its normal operating load. Because the grid has a finite short-circuit capacity, this sudden, massive draw of current creates a rapid, localized drop in voltage at the point of connection. This voltage sag doesn't stay isolated. It propagates through local busbars, and if the dip is severe enough, it can cause sensitive industrial equipment at neighboring facilities to trip offline. To prevent these disruptions, grid operators require rigorous power quality and compliance studies before they will grant any large generation site permission to connect. If a project fails to prove it can manage its inrush currents, it cannot be energized. The result is stranded assets, millions in frozen capital, and extensive commissioning delays. Connecting modern renewable sites means we have to accurately predict and manage the microscopic magnetic physics of individual transformers to maintain macroscopic grid stability. In the UK, the primary regulatory framework governing these voltage fluctuations is Engineering Recommendation P28. These charts detail P28's metric, rapid voltage change, or RVC, setting the allowable severity of voltage dips. The logic: networks tolerate deeper dips only if they are very infrequent. If events happen regularly, the voltage floor is heavily restricted. To prove compliance, developers must model their sites against worst-case assumptions in Section 6.4.2, including minimum fault level. The most critical constraint is Item B, assuming every transformer holds 0.5 per unit of remnant flux before switching. Modeling a simple transformer under these parameters ensures a wide margin of safety for the grid. However, when applied to a large site with dozens of transformers, these compounded assumptions create a mathematical roadblock. The P28 standard acts as a rigid gatekeeper. You either prove your site meets the envelopes under these exact conditions, or you don't connect. To understand why compliance is so difficult, we need to look inside the magnetic environment of the transformer core. The relationship between the magnetic flux in the core and the current required to generate it is described by the BH curve. Under normal operation, this relationship is mostly linear, but when a transformer is disconnected, the voltage wave stops, and the iron core retains a magnetic memory of that final moment. This trapped magnetic field is known as remnant or residual flux. These 3D surface plots map how inrush current magnitude is probabilistic, dictated by the collision between the trapped residual flux and the closing angle. The worst-case scenario occurs when the breaker closes where the newly applied flux pushes exactly in the same direction. When those two forces compound, the total flux breaches the knee of the BH curve. The core physically cannot hold any more magnetic flux. It enters saturation. In this saturated state, the core's relative permeability drops off sharply. The magnetizing impedance collapses, and the transformer pulls a massive surge of current from the grid to maintain the required flux. Because of the initial flux offset, this surge is highly asymmetrical, often carrying a heavy DC component that can linger for tens of cycles before returning to a steady state. The inrush is not a fixed equipment specification. It is a highly variable physical event, dictated entirely by the timing of the breaker and the magnetic history of the core. Now apply that physics to a modern hybrid facility, which might utilize 16 or more medium-sized collector transformers connected to a main busbar. Energizing all 16 transformers simultaneously compounds the probabilistic risk of hitting maximum inrush. Doing so guarantees a massive voltage dip that completely breaches the P28 limits. The forced alternative is sequential energization. Operators must close the breakers one by one, managing the inrush of each individual transformer. This table defines the Category 2 RVC limits for infrequent events. Under these rules, the grid operator permits only 4 switching events per calendar month. The critical restriction is found in Note 2. It clarifies that only one of these events is permitted per day, and each event can contain a maximum of 4 RVCs, meaning 4 individual transformer energizations. Because of this daily ceiling, a site with 16 transformers can only legally energize 4 units every 24 hours. This creates a significant commissioning hurdle. Even in a best-case scenario, the 16th transformer cannot be energized until the 4th day of the sequence. For battery energy storage systems designed to provide fast frequency response, which require frequent transitions and rapid deployments, a 4-day power-up sequence is an operational impossibility. This bottleneck is a direct result of applying strict single-asset regulatory assumptions to the realities of modern multi-transformer generation networks. Bypassing this bottleneck requires abandoning passive switching in favor of active precision mitigation hardware. This technical document introduces one of the most effective solutions, point-on-wave, or POW, switching controllers. A POW controller actively monitors the voltage at the time of de-energization to calculate the exact residual flux left in the core. When it's time to reconnect, the controller waits for the precise millisecond on the voltage wave that will match the prospective flux to the residual flux. By matching the magnetic states, the controller prevents the total flux from breaching the knee of the BH curve. The core never enters saturation, and the inrush current is neutralized. The traditional mechanical alternative to this is the use of pre-insertion resistors. Pre-insertion resistors physically dampen the surge by placing resistance into the circuit for a few milliseconds. While effective, they require an extra circuit breaker, adding significant cost, mechanical complexity, and a much larger substation footprint. Point-on-wave relays, conversely, are compact, solid-state devices. They can be retrofitted or integrated directly into standard switchgear without expanding the physical site footprint. By digitally calculating the physics in real time, these technologies turn a probabilistic magnetic gamble into a highly repeatable engineered process. It is worth addressing a common misconception in the industry regarding this process: the idea that grid support equipment like STATCOMs or battery inverters can stop transformer inrush. They cannot. A STATCOM has no ability to prevent a transformer core from saturating, nor does it stop the initial surge of current from being drawn. What a STATCOM actually does is rapidly inject reactive power into the local network to support the system voltage. It effectively masks the voltage dip at the point of connection, even as the transformer pulls its heavy inrush load. Point-on-wave switching treats the cause of the problem at the iron core. A STATCOM treats the symptom at the busbar. Navigating grid connection is a straight line from understanding the microscopic saturation of a BH curve to meeting the macroscopic requirements of a P28 compliance report. Executing early-stage probabilistic studies allows engineers to identify the 4-day Category 2 bottleneck long before equipment is ordered or concrete is poured. Understanding the mechanics of the surge and deploying the exact active tools needed to manage it is the dividing line between a stalled development and a fully connected operational site. By mastering the transient physics, we ensure these large-scale systems can be integrated into the grid exactly as intended. So plan early, study the transient, energize with confidence.